Yeah.
Yeah, yeah, cloud.
Okay. All right. Hi, everybody. So welcome to our 33rd PyDataTT meetup. All right. And today we're gonna have Mr. Torian Dyer talking about introducing zero code change acceleration for pandas on NetworkX. So he's a senior technical product manager at NVIDIA, and also joining in will be Donna Costa, who's also senior software engineer. All right, so before we start, let's just go over the code of conduct for PyData. So basically, where you need to be kind to others, do not insult or put down others, behave professionally, and remember that harassment, sexist, racist, or exclusionary jokes are not appropriate for PyData TT on focus. So all communication should be appropriate for a professional audience, including people of many different backgrounds, sexual language, and imagery is not appropriate. PyData is dedicated to providing a harassment-free community for everyone, regardless of gender, sexual orientation, gender identity, expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of the community members in any form. So thank you for helping us make this a welcoming and friendly community for all. And now I'll pass you over to Torian and Don to take it away.
All right. Hey, everyone. My name is Torian Dyer, and this is my friend and coworker, Donna Costa. And today we're going to talk to you about a few new, not necessarily libraries, but extensions that have been added to the Rapids ecosystem that allow for a zero code change experience of your Pandas and NetworkX workflows. This is going to be light, it's going to be fun, and hopefully very hands-on. So if you have your own workflows, please do bring them and share them via Colab. We'll be able to run this on Colab now, thanks to Colab now pre-installing cuDF onto the systems. It'll be cuDF version 24.4. So that'll make it really easy to at least do the Pandas version of this. And when we get to the NetworkX, we will run you through how to install and load. All right. Is everybody ready? All right. I'm going to take that as a yeah, and let's go. Okay. So we've gone through the welcome. We're going to briefly reintroduce those who don't know what Rapids is to Rapids. We'll talk a little bit about that cuDF.pandas, that NetworkX. We'll also have a great time with Don learning how to apply graphs to our workflows. Graph analytics is a really amazing field. I fell in love with graphs in my graph theory class back in college. And the capabilities and power that you can by just manipulating and shifting the paradigm shift of like manipulating and shifting the way that you construct your data frames to allow for graphs to kind of take over and show their power, it brings some really cool results to it. And then finally, as this is part of the 5 Islands Hackathon, some of our data sets are there and we'll be pushing it. We're going to introduce that hackathon a little bit while also saying, hey, you know what? You might be able to use this to get ahead and win some of those prizes in that hackathon. So I hope to see you all there. So stop me if you heard this before. Not you, Chris. Rapids is an ecosystem of libraries that allows you to GPU accelerate your existing PyData data science pipelines. 1 second, I'm going to bring it in. Yes. Just checking the chat. So here we have your whole pipeline of data prep, model training. There's some visualization, and of course, what you do with your models after. We all know and love our pandas, our scikit-learn, our NetworkX, and our GeoPandas, but they have hit certain walls as it comes to CPU compute. By vectorizing some of the algorithms and putting them on a GPU and allowing them to run, while also allowing there to be a unified memory management, we have been able to see anywhere from 5x to almost 25,000x speed up of some of these, ETL and data forming processes to machine learning algorithms to graph analytics outputs. And we do this by, as we introduced it, by, I know people are going to be hitting the admit buttons, by allowing for, by doing a changeover between the libraries. So we tried to make it very API familiar and very API similar to the standard PyData stack, so to make it really easy for a data scientist to use. So cuDF is analogous to pandas, cuML is analogous to scikit-learn, cuGraph is analogous to NetworkX, and cuSpatial is analogous to GeoPandas. We also have some of our own awesome libraries like cuVS, which accelerates vector search, and cuCrossFilter that accelerates data analytics. And this all goes to that GPU memory, and because of the fact that everything is in a unified memory format, there's no read-write copy issues, latencies, I should say, so it goes stupid fast. As you can see, we've had some really interesting end-to-end speed ups, and you can join our community. And we did all of this to get to, come on, buddy. There we go. We did all of this to get to this goal of saying, hey, listen, you start your work, get your work done faster with better insights, better results. So you spend more time doing something with your results than sitting down and waiting for your results to actually show up. And we all know and we all love it when we find errors in our code or we think of something else in the mid process and we have to make changes. Well, guess what? In this work, the person who's using the GPU power workflow will get it done, generally get it done faster, get a better model out of their code, as well as get their insights, be able to ask first, second, not just the first order questions, but also the second and third order questions. And that comes from obviously the speed up that you get because your stuff goes from quite literally at times 2 days of processing to 20 seconds of processing. And you'll see some of that today in, well, we're not going to do the 2 day, but we'll do something pretty long. However, oops, I missed something. Oh, that answers that. However, that doesn't mean that this nirvana we've built is perfect. Even though we did accomplish our goals of making this faster and getting a massive API similarity, cuDF, having the largest API similarity of all pandas-like libraries of 60%, it doesn't get us everything. And so we've listened to our users and we've heard some of your challenges as we go over the last, 5 years? So among them are, sometimes you get errors while doing your ETL and you're like, hey, wait, this kind of works, but then it just fails, right? Like here, we can do apply, but we can't do a group by apply, but we can't do a group by filter because it's not yet implemented. We don't have that 100% coverage. And another challenge that we've seen that people, the community youth have come to us with is that, hey, now that I got my ETL going and it's amazing, but it's a little bit difficult to now stick it back to my familiar, tools, my post-processing tools like visualization libraries, such as Seaborn or Matplotlib, or, well, we got Plotly working in HoloViews, but like Seaborn or Matplotlib. And we heard that, like that. We have a visualization guide, and we have a few other things, but it is not necessarily everybody's like, oh, I got to learn this. That takes work. Work is bad, blah. But the other thing is that this affects all alternative pandas-like libraries. Everybody has the same challenge. So starting with cuDF.pandas, we wanted to see how we could fix this in a certain way. How could we really make this faster and easier for you, our users, to bring your current workflow that you are doing right now and pop it onto either a notebook or a script and use both a CPU and a GPU to make this thing sync? What we came up with was, hold on a second, I'm realizing that some of my slides are hidden. So we're gonna unhide everything. So we came up with this extension called cuDF.pandas. And what cuDF.pandas does is it takes your pandas code and runs both CPU and pandas and GPU cuDF acceleration. And at GPU cuDF acceleration is all on top of CUDA. So for those of you who are interested in finding out a little bit more and reading up on cuDF.pandas, you are absolutely allowed. You can take that link. I will drop it into the chat right now. And we'll get into it. Whoa. So, all right, cool. You've got this new magic potion thing, guy. Well, how do I get started with it? Well, we made it pretty easy. You just have to install cuDF. It doesn't matter how or where, because you can install cuDF without a GPU. Thank you. But you can pip install it, con install it, docker install it, and you can get all of that from our install release selector, some of you know and love. And then we've made it really easy for you to actually, quote unquote, convert your CPU only code into a CPU GPU hybrid acceleration environment, which is you could either, depending on where you're running it, you can load this extension either as an option using -m cuDF.pandas in Jupyter Lab, where you can load that extension at right before you import pandas, and it will then start working. And if it doesn't work, because of what your environment is, you can just import cuDF.pandas, and that will just brute force it through. So how does this magic thing work? Well, let me show you. And while I say let me show you, what I'm going to do is I'm going to share with you a quick link. And all of you will be able to kind of run and follow along with us, okay? Since 2 new people did just join, I'm going to resend that link one more time. Oh, Chris, man, some direct message. Anyways, so I believe now everybody should have this link, and that will take you to our example notebook of cuDF.pandas. But let's talk a little bit about what's going on. So first things first is this is a Jupyter Lab environment, because we can see that we're loading the extension with the magic command. And then, as normal, we import pandas, we import NumPy, Seaborn, Matplotlib. We do we create a time series here. And then we do some analysis, because we're filtering the data between 9:30 and 4 p.m. We do a group by and mean, and then we plot the results in this. So to do all of this, how does cuDF.pandas change what's going on? Well, it's all in the back end. So first, when we load the cuDF.pandas, we now look at these import statements, and we say, okay, these are third-party applications and libraries, and this is your code. And every time you call pandas, this library, our extension takes a look at what is actually being run. So when you're doing, when you're creating the pandas data frame, instead of it immediately defaulting to pandas read CSV, we take a look and say, hey, listen, pandas, cuDF.pandas says, hey, listen, is this a supported function within cuDF? If yes, send this immediately to the GPU. If no, copy that to the CPU and run, and then send it to the GPU again. Because this is pretty fast, these are pretty fast operations, and computing on CPU can be slower. And we say can be because sometimes, if you have a really small data set, it's not. So read CSV on a massive data set. We've got 1 million periods because why not? Well, guess what? It's supported on GPUs. So this now runs at near cuDF speeds. So you get the full benefit of reading the near 15x speed up of reading information from a data frame into information from a data store to a data frame that cuDF provides. And then, of course, we have, the certain functions that are not enabled in cuDF. So that then takes the CPU approach. So we have that data using our unified data memory format, and we allow pandas to, once it fails in GPU and there's a fallback, then it goes to the CPU to be processed, and then the results are then sent back to that GPU. And then we get the results again, and this cycle continues until the entire workflow is done. Okay, so I know that this is a little bit different, so I'm going to pause here for questions. Does anyone have any questions on what's going on?
Not that I do.
All right.
Can you hear me?
Yeah.
Oh, so the question is, this will have to be, you'll have to have a GPU to use this. If you don't, you'll have to go to the normal pandas instead of using cuDF.
Yeah, so if you don't have a GPU, you don't have the acceleration.
Okay,
So you can actually, and that's the kind of cool thing about it, is you can actually develop on your CPU only machines, and then, accelerate it with cuDF.pandas on a GPU without single line. And if it doesn't find the accelerator, it's okay. It'll keep going.
Okay,
and
so it'll be easy to
always fail
transfer.
back to pandas.
It'll be easy to transfer afterwards.
Exactly.
Yeah. Okay. Yeah. Thanks.
Exactly. We're trying to make it super easy for you to bring your workflow to GPU and get the benefits of all the acceleration. Okay.
Sorry, just one quick question, because
Sure.
just looking at the code here, right? So all you're doing is just loading the extensions. You're not changing any other parts of your code, and this
Correct. You are not changing any other part of the code. In fact, if you run it in terminal, you don't even change the code. I'll go back to that. You literally just add this option on your Python file.
All right, great. All right.
Yeah, it's kind of cool. So let me just get a couple of things here. Any other questions? Because I just in case. Nope. All right. Keep moving forward. So what does that get you? Well, it gets you up to 150x speed up that we actually advertise without any meaningful code change or any code change at all in many cases, right? You can see that obviously we can do our join super fast. Somebody sent him link. And also in major benchmarks, you can see that, hey, look, on a 5 GB data set, we absolutely trounce pandas and just about everybody else in this. And there's no code change. So you write it for pandas, you get this, right? You go from literally 36 seconds to 1.9 seconds. And if you really want to be, that you can round up to 2. It's fine. We'll take that. Now, that doesn't mean that we're always fastest. There are certain operations where the fallback to CPU does take longer than if you ran on CPU alone. There are certain operations where cuDF may not fail, but it takes a little bit longer. And, that's part of where in the code, which we'll look at in a second, I know I sent it to you all early, will help you understand what's going on with your processes so that when you go to production, you can go with exactly what is the fastest possible execution path. And that takes us to things that I want you to understand, right? Because I want you to understand this before you go and conquer the world with this. This is a single GPU library. So if you have a cluster, use cuDF. You have to use cuDF, cuDF actually. cuDF is faster than cuDF.pandas. It will always, because it's native, right? It's not trying to do checks. It's not trying to do fallbacks. It's not trying to do a lot of other things that cuDF.pandas is. So as you get tighter, you have more control, just like our C++ library or our Python bindings are faster than our Python library that everyone knows and loves. Just follow Panda's recommendation on immutable operations. As you know, this is an extension, so C library, the C APIs are not going to always work. We have some things that we're still working on, but I think one of the big ones that tends to catch people by surprise is that if you have a model that's pickled in pandas and you bring it to cuDF.pandas, it's a different library and it'll have different encoding, so it won't work. So you'll have to do it from cuDF.pandas and it will read only cuDF.pandas pickled models. And then finally, which is kind of interesting, those global variables, they can't be modified, but they can be accessed during the CPU fallback. Right. And everything here, or a lot of the stuff here, is actually available on the cuDF.pandas webpage and documentation, as it's fully supported by Rapids at this point. Other things are they'll tell you which libraries we found third-party libraries we found to definitely not work, or we're exploring at the time. We're looking and we're counting on people like you in the community to help us figure out where our boundaries are and where we can improve. So, we're always looking for the issues, the trying out of things, the workflows and the success stories, or even the failure stories. We're good with those too. Right? So for Colab.
Wait, just a quick question.
Sure.
I'm sorry, this. First of all, is it okay to interrupt you in between? I don't want to. So, just a quick clarification with cuDF.pandas only works with objects pickled with cuDF.pandas. Is that also vice versa? That if I pickle something with cuDF.pandas, so it wouldn't run unless I have cuDF.pandas?
Well, if you're pickling and unpickling, it's very much dependent on how your environment is set up and the libraries that you use, right? So you can't pickle scikit-learn and then expect cuML to read that as well.
Okay. All right.
Yeah. Okay. So what I'm going to do is, let's go through this. So how many of you have, wait, for Colab, sorry, I didn't finish that part. For Colab, Colab now pre-installs cuDF on all the GPU instances. So if you say, hey, I want a T4, I want a GPU instance, guess what? You can immediately do import cuDF. Or you could immediately do, you know, %, load underscore extension, space cuDF.pandas, and get that, all that speed up right away. So are we ready to see the code in action? Or are you already playing with it in action?
Yeah, all right, already playing with it, yeah.
All right. So
I'm waiting.
we're gonna start off with the 10 minutes because, and I wanted to keep this fast because honestly, I'm hoping that you brought some of your own code to do this and that we would end this off with a screen share. So you can run this as you want, but basically we're going to be loading in what is a 0.5 GB data set, and we'll look at the different kinds of parking violations that are happened. And the first time you run it, it will be in using pandas. However, around here, we restart the kernel and we load the new cuDF.pandas, and we do the whole operation again. And you'll start to see seconds drop to milliseconds. And this is at a small data set, right? This is for us, it's small. So we start hitting things in the gigabytes. You start seeing a greater discrepancy between the times. Okay. And then of course we have this thing called a profiler here. And this actually tells you, hey, how much the CPU or the GPU is being run. So for this particular workflow, we didn't actually have to fall back to CPU. And all of this is built into cuDF.pandas. So, and here's the visualization. Of course, we're still using Plotly Express. No changes, no reforming the data, no anything. It works as if it was a pandas data frame object. So when you're doing your work and, you know, it's something where you're either testing something out and you want to go between pandas and cuDF, especially on large data frames that, you know, or data set sizes, this is a great way to start just trying out what you can and can't do and where it will go. You might get your speed, you'll understand some of the speed ups that you'll get, and then you'll be able to make determinations on, you know, hey, do I want to stay on cuDF.pandas? Do I want to stay on pandas? Do I want to hybridize this, or do I want to do this fully on cuDF and get all the benefits of GPU acceleration? Okay. All right, this is the end of my portion. We're going to jump over to the other zero code change libraries in a second, but I wanted to give everyone a chance for any questions. Or is everybody just running this sucker right now and enjoying themselves? Does anyone need the link? I know some new people came in. Thank you, Johnny. All right. Now I'm going to check down for a little bit, and Don Acosta is going to take you through the nx-cuGraph journey. Take it away. I'm going to stop my share.
Okay. See if I can get the share working here. And let's see there. Can everybody see that?
Yes,
Yep.
you can.
I can see it.
Okay, awesome. Okay, so so I've been working on the cuGraph part of NVIDIA RAPIDS for a couple years now, and what started off as kind of an effort to take the huge, NetworkX ecosystem that had millions of developers active and try to give them a GPU experience that was a very short distance from their CPU experience. So at the time, we tried to mimic the APIs of NetworkX, with always the dream of being able to let people kind of have existing codes, existing infrastructure, and then just kind of run it. And nx-cuGraph is really close to that. I mean, it's kind of, in many places it is completely seamless. So again, cuGraph has a lot. cuGraph tries to support most of the legacy graph formats, data formats. Another plug, just while Python is our primary API, we also have a C and a C++ API that integrators and other sort of users would use as well. So there is a lot of flexibility there, but again, right, to go for the straight data science and the code lists, this is sort of the gem here. So this is a kind of a really small example, but it can get you started in a hurry. Simply by installing it with installing nx-cuGraph with pip or conda, that should work pretty much any Unix machine. And this is a simple kind of 5-line Python. Oops, I'm back to my. Okay. So it's just a simple example of taking a database. Now this data file will show you later the various data sets that we use, but this is several million edges, several million nodes. And this kind of a quick example of just loading it, downloading it, loading into a data frame, loading into a graph, and then doing it between the centrality. And with that file, it can be run at the command line, kind of similar to what Torian was saying with accelerated pandas. You can this part right here. Can you see my pointer? I don't even know if that's probably not there. I guess
I can see your pointer.
Again? Okay, good. So this actually turns on and off nx-cuGraph. So if you were in a CPU environment, omitting this parameter would just run the code with a normal CPU NetworkX environment, and this is what would give you the GPU acceleration. So again, developing in an environment without a GPU would be completely seamless. So just a little bit of the versioning. Well, this part here, the actual ability to run the command line has been available since NetworkX 3.0, but the config package, which I'll show you when we get to the coding examples, that's new as of NetworkX 3.3, and again allows a lot more flexibility. So let's go back to this. So here's some of the speed ups that we've been able to achieve, and I kind of explained to you the three different use cases here. We're using between the centrality as the kind of algorithm example. And by the way, any questions or any comments, feel free to interrupt, please. Anything, if anything's unclear or you more clarification. But so the first example is just a straight CPU NetworkX implementation, and it shows how as we use more of the nodes of the graph to do the between this approximation, obviously the execution time goes up. This is the CPU. This is an example of taking the data, converting it from the NetworkX objects to the cuGraph objects, and then running the algorithm. So you can see that when the data is small and the algorithm is fast, the speed up is still significant, but as you do more and more algorithm dependent work and the data loading takes less time, you can see that the speed up is dramatically increased. So again, this is with loading the data, converting it to cuGraph, loading it to GPU, and then running the algorithm. And this is in and of itself quite a bit of speeding. And this is again, this would be what you would get from the network backend priority cuGraph. This third row, I'm sorry, is actually what happens when you are able to cache the graph. So let's say you have a graph and you wanted to run 10 different algorithms on it. Well, you would pay once for the actual loading of the graph, converting, and then running each algorithm. So as you can see that once you reuse the cached graph, the speed ups are pretty incredible. And again, getting faster as the algorithms become hungrier and hungrier. Now, for the purpose of this example, again, for this data set, this is a patent citation database that has 3.7 million nodes and 16.5 million edges. So this is, for a lot of traditional graph algorithms, this is a pretty hefty use case. And just to give you kind of an idea of the actual hardware used for this example, it's, again, definitely, this is not a cutting edge NVIDIA card by any stretch. This has been around for, I think, do you remember what generation this is, Torian? This is at least 4 or 5 years old.
Yeah, so that's an RTX 8000, probably around the same time I started at NVIDIA. So yeah, about 4 years, four or five. There's like 3 more generations of GPUs since then.
And also just to kind of, again, bring this up, maybe this isn't the greatest time for this kind of a statement, but if you have a low-end graphics card on your machine, that you can still, number one, completely develop with GPU in mind and see what actually the GPU will do. But also, again, the scaling will then, you'll get more performance on your local GPU, and then also have an easier path to just run on the faster one or more industrial strength one. So this is all the graph algorithms that are currently supported in nx-cuGraph. So the centrality ones, which are the ones that we'll talk about most today, are out there. Clustering is, I'll kind of note a little bit how clustering, one of the examples uses clustering quite a bit. But again, a lot of the main algorithms are covered here, PageRank being a huge one. So a lot of it's there. We're working on more and more of them. The goal being to cover as much of the NetworkX algorithm set as we can. So this is a pretty good representative sample. And again, we can, I should probably have the links here, but I can share the links later for where all the documentation is for all this. But so we showed you can speed up. We showed you how easy it is. This is kind of a smaller example, but a very classic social network analysis example. Hopefully I'm not going to, anyone who knows graph analytics, probably this might be a little more boring for but it's, it kind of shows even at a lower level, kind of really what these algorithms can do and why you would even use them. So these are the main centrality algorithms. And while we'll talk about the question of, like, for this particular data set, one of the questions was popularity. This is a data set. I guess I should introduce the data set first. This is a data set that's again a classic in social network analysis, where 26 students in a dorm were actually asked who their first and second preference was for dining partners. And what you can see from the data is the solid lines are first choices and the dotted lines are second choices. And you can just visually see kind of where the clusters are and where the outliers are. I mean, anyone with just 2 edges adjacent, that was the minimum based on the questionnaire that they could have. So, but where it gets interesting is, and especially if you talk about popularity, is who has the most connections, which would be like degree centrality. But there's also other aspects of this, which who's connected to the most important nodes, which would be the cat centrality, and also which nodes actually carry the most weight for the structure of the graph. So removing a node would break the structure the most, and that's sort of what these different centralities they measure different things, but they also answer different questions. So like the questions of influence, which is normally a huge question in social networks. But as we can see with some of the bigger examples, the influence can have a huge impact on the questions that you're trying to ask. So again, this is it's the smallest set. So we'll again kind of look bigger look at the data set. So in this case, the questions, I mean, we saw some of the centrality measures, but how can these kind of map to questions you might really have about this data set? In this case, again, this is a population of a small residential school in New York City, actually. Who in the dorm is the most isolated? Who would be vulnerable to bullying? Who would be at risk if population were to change? And whose voices are underrepresented in the groups? And these questions could all be answered by different combinations, or in some cases, the individual centrality measures. So this shows you what the actual CSV of the data set looks like. See, it's pretty simple. Again, the weights are first and second choices. So again, this is a small set just to kind of explore, you know, what you could, the kind of questions you can really question, the kind of questions you can answer from a graph data set. So these are some of the data sets that we have in cuGraph. We have a data sets API that you can run, but these are also available. These are pretty common data sets. So you can see the scales are dramatically different, and the purposes really of these data sets and the main reason they were even introduced can kind of show you the varying applications of graph analytics. Again, this is the dorm dining preferences that I showed you. It's pretty small. Zachary Karate Club was a little bit larger, still very small, but a large aspect of that was anticipating behavior as a smaller group splinters, like based on strong and weak connections. If a group were to break up, you know, who would be in each group. So these are again, and it's interesting to look at the small groups, the smaller graphs, and when I get to the code, you can run any of these data sets through the code. When it's a small group, you can visually inspect and actually, you know, kind of see how the metrics reflect what your eyes would tell you about the data set. Again, as we get bigger, it's almost impossible to visualize it, and you kind of really are fully dependent on the metrics being correct. This is an astrophysics paper collaboration. It just shows which papers are most important in the astrophysics community. Again, it's a little bit bigger, and the questions you would ask of it, you know, which papers had the most influence, which papers led to the most other papers, those questions like that. I'll talk a little bit more, actually, I'll talk a little more about this, the Enron email network. That was a huge case in the 90s where graph analytics were actually a huge player in how the sort of shadow network of the Enron organization was kind of revealed to be doing a lot of the insider trading and a lot of the collaboration that they claimed, people who claimed they didn't know things, and papers that were sent out that were, people knew about papers long before they were ever sent out. A lot of the graph analytics actually showed how all those things happen. So slightly bigger. Cyber data, that's probably, for large scale graphs, that may be actually the most popular domain for data sets right now. And this particular data set was used for online anomaly detection. And again, the scale here is 700,000 nodes and 2.5 million edges. So again, we're getting a little bit bigger here. Patent citations, again, this is the data set that we used here. That one is 3 million, or almost 4 million nodes and 16 million edges. So again, in the calculations, this is what we'll actually show you in the Colab notebook, and this is a pretty large graph too. But again, the uses for this are chains of patents, finding out which patents are in the kind of clusters of different technologies, to try to find out like which ones spurred the most innovation. These are the kind of questions that you could answer from the patent library. Hollywood, this is kind of a fun one. It's just a network of actors and movie collaborations. Again, pretty large though. I mean, you're still talking about 1.2 million or 1.1 million nodes and 57 million links. So this is, again, the questions about, you know, what actors are the most popular, who did the most movies, which, you know, finding clusters of movies and actors who work together the most. A lot of reasons there. Again, probably another huge domain for graph analytics is street maps. and this is a large data. This is and the OpenStreetMap data set is all the streets in York, and again, 50 million edges, and I have to see what the I keep clicking on that. 54 million, 54 million edges. So that's again another huge data set. And this is the biggest data set that we currently use. This is a 2010, again old, but a lot bigger now. But the 2010 complete Twitter follower map. So again, who are the clusters of followers? Who's following whom? Who are the most influential tweeters? Again, this would be a lot bigger now, but again, it shows the sort of questions you can ask when scale becomes not an issue.
So I'm just going to add a little bit of color to that Twitter one, because we weren't allowed to record or really participate in this, but around the time of the presidential elections, not this upcoming one, in the last one, we started to search, a group, I should say, not us, but a group started to search and see where were the sources of misinformation. And using cuGraph, they were able to actually isolate it. Just looking at the Twitter feeds and the messages sent. That's all I could really say. It was live streamed. And then we said, you know what, it's really good that we stayed away from that, because that was a very contentious portion. But it was really interesting to see and watch the power of this capability and how they formed the data frame from these, this unstructured, even though it was a structured data frame, but it's unstructured data to figure out exactly where sources of information came from. Another thing, go ahead, man.
Sorry. No, I would say I attended a conference that had a similar, and what they actually did was it was all on bot detection. Yep. How could they use the actual tweets and the locations and the times of the tweets to figure out when accounts were being shared and where, so what's actually a bot? If you see a tweet, you see a tweet from Russia 1 minute and then it comes from Florida the next minute, it's probably not the same person. So how are these like shared accounts and again, how accounts actually show up and how they propagate through different groups of chat groups, kind of shows how they use algorithms to permeate the different communities that they're trying to turn against each other or form opinion. So
and then there's in healthcare, there's a lot on cancers, genomics, research on propagations of diseases, research on, genus and species. There's also urban planning and development. There's agriculture, there's logistics and shipping. There's quite a few different places that you can actually take a data set that as long as you know that you can form it into a graph itself, right? Some sort of input and output, or some sort of relation that you can figure out. You then can ask these types of questions and get results that you couldn't easily get using standard, non-graph analytic solutions.
And one more quick comment about scale. We have actually scaled cuGraph in some of the over some of the networks up to 1.5 trillion nodes we've run algorithms on. So while nx-cuGraph doesn't scale over multiple nodes yet, we are moving there, and we're trying to kind of converge what you can do with, again, the zero code change NetworkX code, and try to get as close to the upper level of what cuGraph can do right now. So again, the scale right now and the performance right now is much, much higher, as we've shown, but being able to even go across multiple nodes, multiple GPUs on multiple nodes, I think that's a potential that really CPU based solutions right now, at least NetworkX based solutions, single machines don't really have. So that's kind of in the future, but that is the direction that that cuGraph and nx-cuGraph are working together on right now to try to get the scale up as high as we can possibly get it. So I mentioned this is a visualization of the Enron data, which is still on the smaller side of graph analytics, but again, to run the algorithms on a graph of this size, of the Enron size, which as I showed is like, back up here. Oops, I get too far. I probably did tonight. So the Enron data, 80,000 nodes, 6,000 nodes, 80,000 edges. Again, visualization is very, very difficult. You can see the clusters that were identified in this graph, but running these algorithms, especially over and over again, and when the goal was to sort of find similar networks within the larger network, running these things hundreds and thousands of times, I mean, it could definitely benefit from GPU. And again, this is a pretty old case, but it was an example of graph analytics leading to millions and millions of dollars of fines, many convictions, and really ultimately the bankruptcy of Enron. So this shows the data set. It's actually a little small for me. Can you all see this graph large enough, or this basically shows I'm sorry, you guys, okay. This shows the speed up, basically a speed up as a function of the different data sets. So again, the algorithms, it shows different algorithms and the different data sets. So these data sets are from smallest to biggest. And you can kind of see how the different algorithms, weak connections, core number, page rank, Jacquard, breadth first search, and single source shortest path, how they vary and how the performance is increased with the different size data sets. So so again, this is actually a little bit older of a GPU as well. So again, with
that one's only 2 generations. Well, 1 generation behind. That's the hold on one second. That's the one that came after the RTX 8000.
Okay.
The TT Lab has 2 of them in their cluster.
Actually, I think I have a 6,000. I think that's what I have. So so again, and this is sort of the other the GN where cuGraph, a lot of the cuGraph team is dedicated to better support of GNNs. And again, you can see some of the speed ups here, and we do have PyG and DGL interfaces right now, and we do work very closely. Again, a lot of our effort right now is going towards running larger and larger GNNs, and in fact, the 1.5 trillion node that we demonstrated, that one was GNN related. So that's kind of where we're pushing the envelope right now.
So just out of curiosity, by a show of hands, how many of you know what a GNN is? Just raise your hand. Just a poll. Only 2 people? Oh, 3.
Well, we could definitely do a talk. I mean, I would imagine that GNNs would be an interesting topic for a later meetup.
All right. How many people would like that?
Well, I don't want to volunteer for anybody for anything, but we definitely have the resources.
I'm just kidding.
So
all right, future talk.
That's the end of the slide presentation. Anybody have any questions or comments or?
Do you want to show them the? I sent them the link of the actual notebook.
Okay.
Do you want to just walk through that a little bit?
Sure. That was so.
And of course,
this is
ask any questions.
Sure. Are you can anyone see this?
I mean, it's really small, but I know they send the link, so.
Better now?
Yeah, I can see it.
Okay, good. Stop it. All right, so again, the 3 things we'll cover is basically just kind of the setup that we showed in the slides, but actually in the notebook. Then we're going to show the code implementation of the very small data example that I used, the dorm rooms, and how those calculations are done. And then we're going to go into, I guess, what really would be a probably medium to large, maybe large size, but the patent citation data, and run an algorithm on that. So that's sort of the structure of this notebook. So first thing we'll do is we'll install, this might take a couple minutes, or take a minute. We'll install nx-cuGraph.
Now, just to be clear, you'll see that it is equal to 24.04, just like cuDF. You want to make sure that it is equal to the version that is installed currently. If you want to update it, you'll have to update cuDF and nx-cuGraph at the same time for this to work on Colab.
Now we're installing. Again, we haven't installed cuGraph because the NetworkX nx-cuGraph calls that behind the scenes. So this is where we're actually setting the two parameters that this parameter here turns on cuGraph as a backend, and this, which gives us the speed up that we mentioned earliest with the actual algorithm running. This caching, and I'll show you, it's funny, I'll show you some of the warnings that you get because the caching is turned on, but the caching gives you the ability to run the algorithms. In this case, we're running several algorithms that will take the graph, and NetworkX will leave the cuGraph graph out there so that it can get benefit from using that, from not having to reload the graph every time. So again, more packages to install. Okay, so this is a pretty easy method. This is the method that actually calls all of the NetworkX algorithms. We're calling degree centrality, betweenness centrality, path centrality, page rank, and eigenvector centrality. And this is the print function that pretties it up. So this is the ugly one. This is where download. Well, I'm sorry. This is the short file. So this will be quick. So this is what the data frame looks like for that small data set, the small dorm data set.
So, and just to remind you that weight is basically that person's preference in order between the two parties. So the first one is the person who's being asked, and the second
person choice
is their choice, and third one is where they rank that person in their choices. So it's only the top two, as you can see.
And here are the edges in the graph. So every two students in the dorm that mentioned each other are listed here. So this is where it's going to compute. And again, this is wicked fast because it's a tiny little graph. But I think this is what I was talking about, the warnings. So since we do have caching turned on, it kind of barrages you with this warning that, hey, if you change the graph after loading it, it's not been, since the graph is cached, you'll get improper, inconsistent results. And I think it seems a little overboard that they send the message over so often, but it's the way it works. So these are the centrality measures. So if we could, if we looked at the original graph, so like, for example, Eva is right here. And then if you go in and look, and she's pretty much at the top of every metric, not a big surprise, right? Marion shows up very at the top of almost every metric. And if you look at Eva, she has a lot of errors coming in, which means she's very, there's 5 people who chose her as their favorite dining partner. So again, I think the small examples are good because they kind of give you a trust in the algorithm. They show you that what your eyes are telling you is what the algorithm's telling you. So I think that's the main reason. It's not all impressive that you can run a graph with 26 nodes in it, but I think it is interesting that the calculations do reflect what you see. So we won't be able to visually inspect the patent citation. So again, this is an example. We put it in a notebook. I'm sorry.
I said it would just suck. And this is a great time to plug in packages like Graph History that does allow you to visualize large graphs. Leo's a good friend of Rapids. And I'm talking about millions on that order of magnitude of edges and nodes. And it'll help you explore. Their cuGraph and is already baked in. And that's literally how you're able to do some of these larger data sets and validate things.
So, and this is an example. I put it in the notebook so someone can just cut and paste it into their environment and just see it run. And again, you could swap out a different algorithm if you just wanted to see, and running it with or without the priority can show you pick your favorite algorithm, pick your favorite data set, and you can kind of get a feel for the speed up just by just cut and pasting a couple things. So I think that's kind of useful. Now this will actually take a while. It's downloading the file, downloading the site patent citation file.
So while it downloads, does anyone have any questions or thoughts? I know graphs are new to many of us, and it was exciting for me to see it again.
Yeah, I said I'm a social network junkie from years and years ago. It's really, to me, it's really interesting because a lot of the questions that you don't even think about asking of a graph. And again, I can go back while we're waiting for this. I can go back to to this graph. You can ask questions, and this is kind of what I talked about. I have a blog that if I can plug later, or someone wants to send me a message, I can send it to them. But if you want to ask questions of the graph, like what happens if Adele leaves the dorm, right? How will it affect the rest of the organization? Who then is left as potentially unrepresented, or who then only has one or two connections? There are bigger networks removing nodes, adding nodes, predicting. With clustering, you can predict if this organization were to break up, into two dorms, for example, or even two teams, right? Who would be on each team, and the different algorithms can kind of predict that. And again, with a small graph like this, you could probably draw a couple partitions and probably get it close to being right. But with 100,000 or a million nodes, or again, when you start getting back to like the Enron data, being able to optimize clustering and actually find out how these groups, what does this group really mean? If you find this green group, what does it mean? Is it the administration team? Is it, is it the management? Is it, the carpool, right? These colors probably do mean something in the Enron hierarchy and were used to analyze the whole organization. So these are things you can get not just from the graph as it is, but to predict changes as a network grows. You can kind of predict, even find missing links within graphs. I mean, one experiment I did with this just to see if I could do it was to, could I try to like extend this to 3 dining preferences just by looking at who's a friend of a friend, and if they had a third choice, who would it be? And a lot of algorithms do use, recommender systems would at a higher level do things like that, just deciding who likes whom, and therefore who might like somebody if they don't know them right now. So
another thing to remember is can you go back to the slides?
Oh yeah, I'm sorry. I thought I was killing time.
You are.
No,
Don't worry, you're not just killing time. But
while the loading file was loading.
So one of the cool things is, can you go back to slide 3? I think it was for you, the one with the big chart table. Slide 3. Yeah, 4. Sorry, 4.
Sure. There you go.
So one of the cool things about it is that if you look at this, if you did this with pure NetworkX, that's a 3-hour challenge to find between the centrality between for at 1,000 node level, right? It's 13 seconds, 14 seconds, if you will, to do that with nx-cuGraph, or 30 seconds. What this means is it actually unlocks a whole new level of analysis and makes it reasonable for you to try it out. Okay, these things used to take months back in the day. We're now doing it in seconds. And this is just nx-cuGraph. If you actually use cuGraph itself, it would be faster than this.
And we would actually do some hypothesis testing on graphs. We would say, we think this person is connected to these 2 or 3 other people, but we're not sure. Let's make the connections, rerun the algorithms, and see what happens. Does it change command and control networks? Does it vastly change the clusters? Because I mean, often it's easier to know what data is in a graph than it is to know what isn't in a graph. I mean, again, the small example is 100% complete data, but most data sets aren't complete. They tend to be dirty, and finding bad data and finding missing data can be very difficult. So often, again, when you can run the same algorithm on a graph 100 or 1,000 times, it gives you the chance to test out changes and test out theories, even merge 2 data sets and see what they look like. So that, again, it's very difficult to do if you're waiting 3 hours per run.
Nice.
So
Let's see if that download might have finished. Keep going, Johnny.
yeah, it's
no.
done. It's done.
Yeah, it's done. It took just a minute.
Yes.
So a good example to use this is, well, I guess supply chain, to see, if this supplier fails, this gonna take us back a couple months. So we should probably have a backup, something like that.
Yes.
Okay, cool. Thanks.
And another thing we used to do was we saw people showing up in different places, but we didn't know how they got from point A to point B, right? So trying to figure out by what we know about the road networks, right? We know the road networks. We know a person was in point A and point B 2 days later. How did they actually travel? Like you said with supply, again, what happens if a road closes? What happens if you have 3 days to do something versus 2 hours to do something? And you can just run, again, there's tons of algorithms like that you can run for questions like that are just so much faster when you can just run them on GPU. So this is the method that runs all the algorithms. And now we're actually going to run them. And this should take about, I think it takes about a minute. So this is where we compare it to what it took with just the CPU.
Yeah. And so back to opening the questions again. Otherwise, we'll watch the spinning circle.
Yeah, this is it does take a little while to run it, even on GPUs.
Yeah. Here's a big question. A lot of these are preformed into graphs, right? Into a destination and an edge node, right? Does anyone have any thoughts or ideas? And I know this is going to probably come up later once we turn off recording. Does anyone have any thoughts on like some of their data sets that they would want to see that they would be able to convert to graphs, like, or any questions on that? Because it's kind of interesting, like what you could actually turn into a graph, like parts in an assembly, if you will, for manufacturing and machining, shipping, flights, travel, location to genus or species of plants, if you will, or bugs found, or what kinds of bugs are on plants and what's their relevance. Like you can go all the way down and go all the way back up. So what are some other things you're thinking about?
So we finished.
Oh.
And between this took 26 seconds. Breadth first search took 47 seconds, and the Louvain took 50 seconds on that size data set. So,
all right, and let's compare it to the CPU. So you'll notice that sometimes we're not the fastest.
Again, loading into a GPU is not free.
Yeah.
And BFS really isn't that big. Let's see what costly that. What was it? So that's kind of all I had. Again, any questions or any algorithms that maybe you think would be good to show, or maybe, I mean, we are adding algorithms fairly often, and again, always trying to optimize them as well. So
just to for sake of time, I'm just gonna go and plug the hackathon. I'm gonna share my screen, like on video.
do I need to stop sharing?
I'm gonna replace the current share. Don't worry. All right. So for those of you who don't know or do know, the Five Islands campus of UE is having an AI hackathon, and we'll be doing data science. We have a set of large data sets, that some small, some large, for beginner, people who are just interested in seeing what is all this data science thing about, or trying to wrap their heads around some, data analytics to higher end understanding of their data, to experienced folk who are just like, yo, I'm gonna make this data tell me exactly what I want to say, right? Wanted to say, and get the insights out that I need, where they're gonna be doing things from, applying advanced techniques to even, and I'm really curious to see if somebody would love to take the data and use it to do some RAG on an LLM, which I think would be kind of cool. The patents data set is going to be one of them. There's also some AIS data, some crash data, and I'm missing one of them. Oh, the power generation data, but each one of them is a large data set from abroad, but can be easily applied to the necessary challenges and problems that the island communities do face. So I encourage you to, one, sign up for this hackathon. If you are so enthused, be a mentor or a judge. And two, especially for the larger data sets, to reasonably win, you're going to need to use GPUs. You're going to need to use what was shown here, because as you see, you don't want to be 2 hours into your data set and then realize into your processing and then be like, oh man, I got to run it again. You'd probably want to do the 23-second version of the same exact code. Or, instead of like a 5 or 10 or 15 or 30-minute read, you probably want to do the 2-minute read or less. So that's part of the reason why we wanted to show it. And I know it was a rushed output, but this is why we, part of why we canceled the original one, because we wanted to make it a little bit more applicable to what was going on. And this is why it was opportune, because now you have a leg up on not just this hackathon, but almost any other hackathon you want to jump in on. You don't have to know any specialty coding. You don't even have to be quote unquote deciphering which algorithms or which functions actually work in terms of doing ETL on your data frames, or trying out this new capability for graphs that will help you get even better stuff with GNNs. You can just bring it in as it is, bring in your workflow or your thoughts, write it where you want it to be, and either as you're accustomed to in Pandas and NetworkX with full code, and then of course GPU accelerate that action with cuDF.pandas or nx-cuGraph. So I look forward to seeing you all at the hackathon or at Five Islands. At the conference, I will be there. Bring milkshakes. It will make me happy, and I promise I will talk to you longer. No, I'll still talk to you. But and I look forward to seeing your presentations, especially for those of you who submitted something this year. Oh, and I'm supposed to be at the opening talk. I'm supposed to say that. Yeah, I am talking at the open. So without further ado, I will pause. Does anyone have any questions or comments before I end recording, or would you rather, and you can send it in the chat, have me end recording and then we just go to the line at the end? Okay, there's a question from Nicholas Smith. Don, if you want to take that, or do you want me to take that?
Let's see. I didn't have the chat open. I thought they were going to ask it. Let's see. Absolutely.
Oh, wait, let's
Page
grab the question.
Okay, I'm sorry. Can you use graphs and recommendation systems for collaborative filtering? Yeah, I mean, absolutely. Again, PageRank is one of the biggest recommender system algorithms that are out there. But yeah, graphs definitely have a place in both those functionalities. I'm not as, I mean, I've messed a little bit with collaborative filtering, but I know that there's definitely graphs have a place in that, because I did some of that with the Neo4j. I was mostly doing the graph building at the time more than the algorithm writing on top of it, but I know that was definitely a thing.
All right. Any other questions typed or asked? All right, we'll turn off recording in a second. Let me close out. I want to thank you all for coming to the PyData Trinidad and Tobago 33rd presentation. I'm going to say this straight. I was going to send you all an email, but I know that it has taken us literally a half a year between meetups. Guess what? We've got a packed next half of the year. We're going to do all those meetups. And we're excited to see it. There's going to be a mix of both specialty content, as well as interactions with different kinds of groups, and local talent, talking and showing off what we can do as Trinidadians. A lot of this has been on us building the relationships, as we talked about in the final in our end of the year meetup. People wanted us to collaborate a bit more, and so we are. So we want to thank UE Five Islands Conference for joining us and allowing us to present. We had one of the hackathon presenters there here today, Dr. Ilpit. Oh man, I'm gonna get his name wrong, and it's gonna be fun. Ildefons, Dr. Ildefons. I'm sorry, man. I just wanted to make sure I pronounced it correctly, but he was joined us today. And we want to give thanks to him and the entire UE Five Islands Hackathon team for putting this together. We're going to try and do more social things over time. We're also going to try and make sure that as we hit this new wave of generative AI, that there's going to be content towards that, so that you can apply both your machine learning, your data science, and your Gen AI towards the whole scope of things that all islands are going to be facing. So thank you again for coming. Thanks for your patience. And we look forward to our next meeting, which Jodan has something as an event on the 5th, which is still this week. Like I said, we're going to be packing it in. That is, I'll send the details in the chat to keep going. All right, we're going to end it here. Thank you so much for everything, and I'll see you next time.